Hi, everybody. Thanks for coming to this talk. Today, I'm going to talk about high performance Rust UI. So this is work that really I've been doing for a very long time, and it's an exciting time in the project. So I really wanted to update people on what's going on, a little bit about what the vision is for the future of this. So in this talk. I'll talk about the goals and motivations of the project, which is really focused on performance. The reasoning of why we're rethinking the entire stack as opposed to just sort of optimizing one piece of the stack at a time. The layering, the deciding where the architectural layer boundaries go profoundly affects the performance that you're going to get of the complete system. I'm going to go into a fair amount of detail on the drawing layer, which is piet-gpu, which is a 2D rendering engine that really leverages GPU compute shaders. I'm also going to talk about the reactive model and the goals of enabling Rust async in that. So that's going to get us into the Xilem architecture, which is kind of a new architectural direction that I'm very excited about. Talk a little bit more about that 2D rendering engine. Talk about the idea of the way layers work. And then, this is all very much work in progress. I'm going to talk about, kind of the next steps of that work. So a little bit of history here. I've been thinking about how to implement UI in Rust for at least since 2016, the Xi Editor project. And so a lot of the work that I'm presenting today is an outgrowth of that work. It was a very, very different architecture. The idea of having multiple processes that are separated and talking over communication channels, so that required it to be very async. And I think the project was not successful, that the async nature of it added a lot of complexity, and we ended up not really shipping a viable editor project. But there were some really good ideas in there, learned a lot, and I think it informed some of the future work. So the next generation of this work was the Druid user interface toolkit. The first version of that grew out of trying to build a front end for Xi Editor. If you look at the Git history, Druid is forked from Xi Win UI, the user interface layer, or the front end for Xi Editor for Windows. The original version of that had an entity component system inspired architecture, and it was very much organized around using the platform drawing capabilities. So if you're on Windows, it would be Direct 2D. If you're on Mac, it would be Core Graphics, etc. The entity component system architecture we found really low level and ergonomic. We couldn't make it do what we wanted to do. I think it's still an interesting direction to explore. I think there are other projects that are based on entity component system, but it wasn't the particular direction that I wanted to go. So the next evolution of that architecture, and this is a little bit of a theme, there's a lot of iteration here. You don't immediately know what you're doing. You have to try something, figure it out, and learn from it. So the next iteration of that was what's now known as the Muggle architecture, which is a mapping. I talked about this some in my blogs. It maps the application data as a tree into the views. And when that mapping is straightforward, when that's a really good model of what the app is doing, then you get really nice patterns. It's really nice to program. But if there are other patterns, like especially if there's dynamic creation of tabs and other user interface elements, it gets pretty painful. This was being developed with the Runebender font editor as a sort of hero application for this framework, and that font editor is now on the back burner. I'm hoping to get back to it. I still think it's a really interesting project, but it's not the primary focus of what I'm working on. And then from that, we found the platform drawing to be surprisingly underperformant. It varies a lot. Core Graphics on Mac is still fundamentally doing the graphics on the CPU. And actually, the reason why you still get reasonable performance on Mac and iOS devices is that it heavily uses the system compositor. So you render the layers in software, and then you use the compositor to scroll smoothly and do all those things. And that's an interesting approach. It works, but ultimately, I decided that what I really wanted to do is do the drawing very efficiently on the GPU, and that has become a major research project. And I'll certainly be talking more about that as the talk goes on. So this is a research project. This is not a product. This is not something you can use today. But it is a research project, and I think that there are some really, really interesting research questions that I want to answer. So the big one is, how much performance gain is possible over the existing state-of-the-art? I mean, a lot of user interfaces that people build and run today have kind of disappointingly poor performance. Why is that? Why can't we build things that are super fast? So that's really, I think, the fundamental question that I'm trying to answer is, what would happen if you just tried to build a user interface that had an incredibly good performance? And then I want to break that down. Like, where are the wins? Where are the performance losses of the existing state-of-the-art compared with what you could do if you were building something that was designed to be performant from the beginning? And part of that is the architectural layering. I mean, we have different ways of, like these, that's moving towards a sort of a web-centered view, where one of those architectural layers is the DOM. And is that a source of the performance problem? I mean, the DOM itself has been identified as something that holds back performance when you build your UIs in that architecture. So what is the right architectural layering so that you can unlock the full performance of the hardware? And then, if you just said, okay, here's a really painful way of writing things in a very low level, so you can do a demo that's super fast, but if you tried to build a real system, then you would find that it was just completely intractable. That wouldn't be a satisfying answer either. So another sub-problem, or another part of the research is, how can you express the UI in Rust excellently? So idiomatically, concisely, and so that you can build components, so the components compose well, so you don't have to be, constantly dealing with the extremely low-level issues about, like, if you have two things on the screen, how are they talking to each other? You want to be able to build those components, and that's very much the trend. Composing is very much the trend of how UIs are being built today. So a huge part of this question of how do you do a performant user interface, how do you build performant user interfaces, is to use Rust. And there's good news and bad news here. The good news is that it is a really good language. It is high level, it is performant, which is key to the project, and it is safe. You don't have to worry about it segfaulting, corrupting memory, all those kinds of things. There's some other really good things about Rust as well, that there's this very strong commitment to portability, that Windows, Mac, and Linux are all first class, and you can compile to other targets, you can compile to mobile, to Fuchsia, and all the stuff really just works. And there's a very active ecosystem. People are constantly building interesting things in Rust. There's tons of crates being developed, being released all the time, if you have special things that you want to do. It is also challenging. I mean, it is not easy to build a GUI in Rust, and I think there's a sense that the space is kind of fragmented, that there isn't a really good solution that's out there, and part of that is the challenges of the Rust language. So the big one is, if you have a traditional GUI pattern, we've been building GUIs for, since the Xerox PARC days, right? Decades. Those patterns cannot be expressed idiomatically in Rust, because those depend on shared mutable state. And, if you go back to certainly the Smalltalk, early Apple, Cocoa, et cetera, those are all based on object-oriented, kind of traditional object-oriented programming with inheritance. And again, you can sort of express those concepts in Rust, but it's really painful. It's not idiomatic. And in particular, shared mutable state, has a lot of problems. It's very clunky. You have to write all these ref cells, and if you do it wrong, it can fail at runtime, which is really against the Rust kind of philosophy. The idea of Rust is get it right at compile time, and then model your problems in the type system, and then when you run it, it has a very good chance of just working. So there's a lot of fragmentation in the GUI space. Have a blog post on that topic. There are some patterns, like Elm and immediate mode GUI are two patterns that are very different than that kind of traditional object-oriented model. And those you can express pretty well in Rust. And so you see quite a few examples of people trying to do that. There's another point here, which I'm kind of not addressing, which is that, the kinds of languages that you think of for writing UI, like JavaScript and stuff like that, come from an interpreted tradition where you can have a edit, compile, test cycle that's very short, almost immediate, hot reload kind of thing. Flutter has that development experience as well, and Rust doesn't really do that. That you can have a slow compile. It's being improved, but it's still. It doesn't give you quite that beautiful interactive, just click something and having come up on the screen. Great. So I want to talk about performance in a little bit more detail, because first of all, it's not one simple thing. There isn't just a single dimensional axis of like how fast does this run. There's actually a lot of different dimensions that you might care about. So the main one that people think about and care about is the ability to do a 60 frame per second refresh, or on modern hardware you're talking 120 frames a second or even higher, and you want to be able to do that without janking, without dropping frames. And you also certainly want to not have user visible, like if you click on a button, you don't want to have somebody perceive that there's a wait until it responds. So another very quantitative aspect of performance is latency. That modern computer systems are not really optimized for latency. It's much more common to optimize for throughput, and latency often suffers. The compositor is a very big source of that. I have a blog post called "The Compositor is Evil," which talks about the way that the compositor adds latency. So in order to build high performance UI, you need to implement some concepts like frame pacing and closer coordination with the compositor to mitigate some of that. And that's a goal. We're not focusing on latency quite so much right now, but it is on our radar. It is on our roadmap. Other aspects of performance that are kind of a problem on a lot of modern GUI toolkits is startup time. You're loading so much stuff. You're initializing all these abstraction layers that have, garbage collected languages and, all kinds of state that needs to be initialized. And so startup time can be slow. And also binary size. It's very related. Again, just a function of how many different subsystems you've got to bring up, you've got to pull into the app, especially if you're, shipping an entire browser in there. So what are the strategies that we're going to use to improve performance? First one, obvious, use Rust. Rust is just a faster programming language than most of the languages that people use to program GUI. So you could get a non-trivial performance improvement just doing the same thing people have always done, just rewrite in Rust. But that's really not where the big gains come from. One of the ones that I'm most excited about is to use a modern drawing engine that is GPU centric, that's really tuned to the capabilities of that GPU hardware. Another thing that's really important is to utilize the threads that are available. I mean, the computer I'm typing on is a Mac M1 Max, I guess it has like 10 cores or something like that. So traditionally, UI is often single-threaded, and so you're really not using the capabilities of the hardware. So what are the expensive resources? Images. You need to decompress the images, and you need to do text layout. Text layout can be pretty slow, pretty expensive, And if you've got, dozens of text layouts in your UI, why not farm those out to the multiple threads and have them join? And again, Rust is a really compelling language for this because you can express those threads safely. And if you're in most languages, coordinating those threads and making sure that you're not getting into complex lifetime problems, then Rust is compelling for this. I want to cut out a lot of the accidental complexity. Again, like shipping an entire browser, there is a tremendous amount of complexity that's in there that much of which is probably not needed. Of course, you also have the essential complexity. You want to support a lot of richness. You want to support all the languages of the world. You want to support accessibility. There's all kinds of functions. If people often have a rosy view of, well, why, we had good UI 20 years ago. Computers are much faster. Why can't we just do that? Well, if you actually try to use those systems today, you would find that they're pretty lacking compared with what you expect. So you need to make a distinction between the accidental complexity that is just layers of cruft and the essential complexity of the stuff that you really want to do. And then another aspect to performance is incremental computation, that there's a lot of wasted work. There's a lot of recomputing the same thing over and over again that's actually the same thing that you computed just 16 milliseconds ago. So a theme of this is to avoid unnecessary work at all levels. So there's a question in chat. I'm going to do it. Feel free to ask questions. I'll address this. Which crates would you recommend for code that works on both CPUs and GPUs today, which are promising in the future? That's a really deep question. There is no crate today that really lets you write code that runs on both CPU and GPU. If you want to write code that works on GPU, you have to write compute shaders. And I'll be talking about this, that WGPU is a really promising cross-platform abstraction for that. So that's kind of what I would recommend. Really excellent for experimenting. All right, what happened? Okay. So a big part of the architecture of the whole system is Xilem, and I have a blog post on this. I'm going to talk about it a little bit here, but I kind of recommend going to the Xilem blog post to get a deeper dive into exactly what's going on, exactly, how the architecture works. Because I feel that Xilem is a way of expressing reactive. I'm focusing on user interfaces. So let's just say expressing reactive user interfaces in Rust that is just as native to Rust, just as concise and idiomatic as, say, for example, Swift UI would be for expressing UI in Swift. And Xilem does draw very deeply on the Swift UI ideas. There's a lot of elements to the architecture that are in common, the whole modeling the UI as in static types and so on and so forth. So one of the claims that I make for Xilem is that it is concise, that there's not a lot of extra boilerplate. And so I give this is the kind of classic counterexample from 7 GUIs. And this is pretty much, I'm actually not going to do the demos today. And when I gave this talk last, I actually pulled it up and gave the demo. The demos are kind of still in process, so kind of watch this space. But this is pretty close to the whole program. I mean, there's like a main and there's like use, but this is kind of the whole thing for bringing up a clickable counter. And so it's really notable for all the stuff that isn't there. Like, for example, if you were in the Elm architecture, then you would have a message data type that would be an enum of like increment and reset and all the different things. And you would have a lot of plumbing of, you'd make the button generate that message, and then you'd have another update thing that would reduce that against the application state. And this is really kind of the simplest declarative way of expressing this, that when you have a button and you click the button, that button has a closure in it. That closure has mutable access to the application state. And then similarly, when you're creating your views It's really this very simple functional thing. The views are simple value objects. You're not threading a context around. There's a lot of stuff that you often see. You don't have explicit IDs of the individual elements in the view tree. There's a lot of stuff that's missing. There's a lot of stuff that's been simplified out, and I think that that's a really good thing. I have a general question. As a render program, I have a hard time adopting Rust. Any comment on this? How's Rust been treating you from that aspect? Um, it's a learning curve. I love Rust. I feel just as productive in Rust as any other language that I've programmed in, including the kind of Python scripty type languages. So I would say stick with it. And as far as WGPU missing some critical features, yes. And basically, I'll talk about this later. We'll go into that in another slide. Great. So again, I recommend people go to the blog post on Xilem. It is, a proposal. I'm not saying it's the end state necessarily, but I'm saying it's a credible proposal for that end state. It's progress towards that. And at the heart, it's an incremental computation engine. So it actually kind of shares some stuff with the adaptons and the salsas, the kind of incremental computation engines that are out there. It's a little simplified. Like, it is tree-based rather than graph-based. So that's not to say you can't have wild edges. There is a way to express. If you want to have an edge from, let's say, the layout in the widget tree back up to the view tree, which is in SwiftUI, that's called geometry reader, you can express that. So you're not strictly in a tree. But when you are in a tree, then those data flows, are extremely straightforward to represent. And efficient, and I think one of the whereas if you look at something like Adapton or Salsa, it's a general graph. So a tree is just one of many possible structures that you might have. And so essentially, my hypothesis is that when you're doing GUI programming, that the vast majority of the structure that you're dealing with is trees, and so you want to make that clean and you want to make that efficient. Xilem architecture is also statically typed. This is somewhat unusual. Most UI programming is very dynamically typed and very loosely coupled. There's a lot of boxing and dynamic dispatch and so on and so forth. And so SwiftUI is definitely one of the most notable exceptions to that. And Xilem really draws from SwiftUI and how you represent, how you model the app state in types. So you have a view tree. The view tree has a type. And then one of the things that's, I think special about Rust is that you have a very sophisticated type system. You have associated types. So if you have a view tree, then you can use associated types to say, automatically infer this is the state, the view state, because you need to persist state across multiple invocations. And this is also the widget tree, and all that's inferred. The programmer doesn't have to write that. The compiler is doing that work for you. And then another thing that, again, is kind of using the Rust type system very deeply and is also very similar to the way SwiftUI works is that there's type erasure, that you can say this is the static type of this entire tree, but you can also have a node that's any view, and then that can be boxed and dynamic. And the type erasure is particularly interesting if you are trying to bind it to a scripting language. Does that mean we get a type that spans multiple screens due to the nested genetics? I think that's a deeper, more complicated question. We do want to do multiple screens, but I don't think that that's necessarily modeled in the type system. So let's just call that work in progress. Great. So I want to talk a little bit about how the Xilem architecture works in detail. There are two associated types. So again, this kind of gets into the the way that we model UI in the Rust type system. So there's view state. So when you create a view is an object that has relatively short lifetime. The app is just building new view trees all the time. And great. I don't. It turns out that question was a joke. I don't always get that just watching the chat. So, um, in any case, yes. So the view state uh, is persistent across multiple view trees, and so this is really important for being able to have continuity. That there is stateless aspects, and then there's stateful aspects, and you use the view state to model that state. And then the view tree, the views are very lightweight objects. They're really just simple value types. They're not doing anything complicated in terms of interfacing with a platform or doing graphics in the views. What they do is that they create and update a widget tree. And the widget tree is the one that's connected to the platform, accepting mouse and keyboard events, and drawing its appearance. So there's three methods. The view trait is fundamentally, three methods, and it's open-ended. So this is something that's actually a little different than SwiftUI, because in SwiftUI, the view is very opaque, and there is a way to do like UI representable or whatever, where you can bring in a Cocoa things, but it's still fairly opaque. If you're building a kind of a native SwiftUI app, then you really treat these views as black boxes. But in Xilem, it's open-ended. And so the build method just creates the widget and initializes the state, and it's usually pretty straightforward. The rebuild method is kind of the core of the reactive nature of this. So you diff against the previous view tree. So it takes the previous value of the view tree as one of the arguments to that method, and it mutates the widget and the state if needed. Like if you don't need to make any changes, if the value of the view is the same, then you just say they're the same. I'm not going to do anything. I'm not going to do any mutations. But if you click the increment button in the counter example, you say, oh, this is a different number than it was before. Therefore, I'm going to do like set string on the label or whatever it is to update that widget state. So that's where the incrementality comes from. And then the third method, and there's a proposal to rename this to message. We'll see. There's all these things are subject to being refined. This one, the details are a little complicated. I'm going to skip over it, but it is basically a way to get events that are both from the UI. Like if you click, the mouse click gets turned into an event, and the event is also used for internal plumbing of various different, internal things, like when you have an async future that needs to get resolved, and other things like that. Okay. There are questions in the chat that are concerned about the performance problems if you are diffing a very large tree. That is a really good point. That is a really good question. Let me see if there's what the next slide is. Okay, I did not go in. I don't have slides for that in this talk, so I will speak to the question. You do not want to build a full tree for the entire app state and diff that tree every time you do an update. That is a performance problem. That is not what Xilem is about. The simplest way to express it is that you do that. You do build a tree, and then you use the rebuild method to diff that tree. But as the app scales, you want other mechanisms to do real incremental computation and avoid that sort of make work of constantly building trees and then diffing them and finding that there's no diff. So the first thing that you do is that there is a memoize node. And the memoize node avoids building the entire subtree. So you look at higher level state in the app and you say, if this state hasn't changed, and that could be a pointer diff. You could very often you would want to have that in an arc, and then you would just use a pointer EQ method on the arc to tell you that nobody mutated that state. Therefore, it could be a very large chunk of state, but If the pointer in the arc hasn't changed, then that's evidence that nobody has mutated it. Therefore, you just don't you don't traverse into the subtree. So that's one of the answers. The other thing is collections, the list views. You have tons of whatever it is. Like in RuneBender, it would be a lot of glyphs in your glyph view. And again, it's the same kind of thing, that the view for a collection is not going to go and traverse and make the views for all the elements in the collection every time. It is going to have a data structure that may be a very clean, beautiful, immutable data structure. Maybe there's a different way you do it. This is part of the view trait being open-ended. There's different strategies in it. The idea is it will support any strategy that's valid. But if let's say you have a nice, beautiful, immutable data structure that's a list. So then you say, here's the old list, here's the new list. What's the diff? What's the delta? So you have to have a smart data structure that's capable of giving you a sparse delta on that. You take that delta and then you say, oh, only these few little children have changed. Therefore, I'm going to go into those and create the view trees and traverse into the rebuild method just on those. So it is absolutely a goal to support fine-grained reactivity and like real incremental computation where you're using some smarts to determine what has actually changed. And for the parts that haven't changed, you don't go in and create the tree and diff them, you skip. Hope that answers the question. So this is kind of a graphical thing of talking about how this flows over time. So when you have the app state, and the app state is sort of in charge of the whole thing. And when you first bring up the UI, it creates a view tree. And that's the build method. And so, yeah, the app creates a view tree. So the app is basically like, give me, the main method on the app is just give me a view tree for your current state. And then once you first get that view tree, you're going to call build, and that's going to create the view state, and it's going to create the widget tree. And those are going to persist for a long time. And then you're going to get events, and events are going to go into the view tree. So this would be mouse clicks or things like that. They're going to go into the view tree, and then those are going to when you call that method on the view tree, you're going to give it mutable access to the app state. So that's going to be able to update the app state. And it's likely that some of those updates are going to cause the app state to need to re-render to build a new view tree. So you get it creates a new view tree. So it's actually creating that tree, and then you call the rebuild method on that, and that updates the view state and updates the widget tree. And so you're going to have like multiple cycles of that. So yeah, there's a couple comments in the chat about state management packages and immutable collections creates. We experimented with this in Druid. I don't think the state in Druid is like really, really nice, but this is definitely work that's planned. And this is stuff that exists in other user interface toolkits as well. I think the goal is to make it clean and to make it sort of the default is performant. That's another way of thinking about it. Like a lot of times you say there's an easy way to do it that's very inefficient, and then if you really want to optimize it, then you take some pain. But like what I want to do is the collection view, the list view by default does this lazy stuff. And doesn't have you build lists and diff them every time. So this is something that is it says demo. I can no, I don't. I don't have this demo prepped, and I see that we don't have a ton of time. I'd like to stay in an hour. So future there will be a blog post, and you'll be able to see more detail on this. But one of the goals is to run things async, and especially to be able to do expensive things like creating images and so on and so forth, that you want to do those. There's actually a lot of different reasons why you do async. There's some problems, like if you're going out to the network to fetch things and displaying it, then you have to be async. There's no real choice. And there's other things where you can use async to be able to farm out expensive work into lots of different threads. So I want to explain the concept here. because I think this is actually pretty, this is a tricky thing, and you really want your UI framework to get it right. So architecturally, I won't talk about the implementation. It's interesting. Like if you're into Rust async, there's a lot of detail that's interesting. So this will be a blog post, I promise. I'll go into lots of detail, but I'll talk about the goal, sort of what you want, why you want to do this, and what you want out of it. If you have something that resolves fast, like for example, if it's a networkable resource, like you're fetching an image, but it's in the cache, then you don't want it to flash. You don't want to have one frame where you've sent off the async request, but then you get a paint cycle, and then almost immediately the async request resolves, but you've still flashed it. So there's this kind of there's a timer internally, a timer. So when you have futures, you send them out to get resolved, and you start a timer, which can be like, let's say 5 milliseconds, so a lot less than a repaint cycle. And the async futures that resolve within that timer, like when that timer expires, or if all of your futures resolve before then you do a repaint cycle. So that causes you to render all of those fast resolving futures without any flashing. But then if there are futures, like if you actually did have to go out to the network, that's not going to resolve in 5 milliseconds. So you paint, and you might paint some sort of spinner or some sort of state representing the fact that there's async work that hasn't completed yet. And so you're not blocking. So there's kind of two behaviors. There's blocking behavior, which doesn't flash, but it would jank if it took a lot of time. And then there's async behavior, which gives you this intermediate state, but doesn't slow down, doesn't prevent the UI from updating. And you kind of want that to be adaptive. You want the blocking behavior when the future resolves quickly, and you want the async behavior when the future is actually going to take longer than a repaint cycle to do. And so this is all tracked internally by the engine, and the programmer doesn't need to worry about it. So a huge part of the work is building a new GPU rendering engine. And you can almost think of Xilem as being an extension, of being something to give an interesting workload to the renderer. And so this is work that I've been doing for many years now, and I'm really excited. I feel like we're getting closer to something that you can use day to day. Not quite there yet, but I think it's within sight. So this is GPU accelerated 2D drawing. It is fundamentally built out of compute shaders, so it's a different approach. Most GPU renderers are built on the rasterization pipeline, fundamentally breaking the scene down into triangles and rendering it with triangles. This is not doing that. This is doing it really in software. It's really a software renderer that's just happening to run on a computer that has potentially thousands of threads to evaluate that. So there's a coarse rasterization phase, which basically builds a command list for each of the tiles. There's these 16 by 16 tiles, and so you say what actually has to happen within this specific tile. And then there's a fine rasterization stage, which just evaluates that command list and operates like super, super duper in parallel. So this builds on a lot of work. This is not the first renderer that has this kind of architecture. There's Spinel, which is also at Google. There's Pathfinder by Patrick Walton, came from Mozilla, and there's a bunch of academic work. And so we're really trying to take that and make it into a really nice renderer. So I have this sort of block diagram of how the very rough block diagram of how this works. That you take the elements, you have this very high level representation of the scene, and you have kind of two pipelines that the path segments are in one pipeline, and you render those into path segments that get tiled. So you basically assign each tile the path segments that intersects with it. And then the other drawing operations, like your gradients and so on and so forth, go into this other pipeline. They come together in this coarse rasterization stage, and then the output of that goes into fine rasterization. So one of the things that is really interesting about this architecture from a UI framework is that the scene encoding, this is a little different than, say, for example, HTML canvas. That in HTML canvas, you have it's a very object oriented. It has kind of to me, it has a very old flavor to it, that there's this render context and you have all these methods on it that manipulate graphic state. So that's part of the problem, that it's too stateful. Like, part of the work here is to make the creation of a scene fragment an effectively stateless operation. So it's just very different in flavor from a traditional Canvas API. And so you're building a tree of nodes. Those nodes look a lot like SVG nodes. So it is very much, when you have a path that's just move to, line to, curve to, very familiar. And then you're assembling those nodes together into a tree. So this tree is also a very important part of the whole structure, because there's blending, and you can have masks, and you can have the blend modes, and you can have, we actually just added a blend group with alpha a week ago. And so you want to have this sort of rich compositing model, which I think really maps very closely to what you want to accomplish in a UI. Also, affine transformation. So when you're scrolling, you just, you don't have to re-encode the contents that you're scrolling. Those fragments, you essentially persist those, but then when you render them, you say, I'm going to put a different transform on them. And that can do scrolling. It can also do smooth zoom and other things. So you're building these nodes, and then the actual implementation, these are simple value types. So you really, it's just doing a binary encoding. It's kind of like flat buffer a little bit. It's an efficient binary encoding. It's variable size, sort of a lot of cleverness in how do you get an efficient encoding that's compact, a very small number of bytes to represent the scene, but yet a GPU can process it in parallel. So there's a lot of rocket science in there. So then the idea is, let's see if this next slide, yes. So the idea is that in your UI, the paint method in the UI builds a scene fragment. So it's very different. Like, traditionally, you have a render context, and it's kind of conceptually painting on a render target. But here, you're just creating a node, in this very efficient binary encoding. So you really just have some sort of you've got a struct that has some vex in it of these byte encoded streams, and then when you're compositing, when you're kind of building the UI, you're concatenating these scene fragments together. And the idea is that operation is super cheap. And then, because these are simple value types, because you're not threading a render context around, if you want, you can just farm that out to multiple threads, and each thread creates its own scene fragment, and then you bring those threads together and you concatenate them. And so, again, as I mentioned, like, changing the transform doesn't require re-encoding, so you can scroll without re-encoding the contents that you're scrolling. And when you're doing text, you can also get scene fragments for those glyphs, and you can re-render them, with different transforms. You can smooth zoom, all that kind of stuff. There's some discussion in the chat about how this will work on, kind of compatibility of compute shaders. WebGL does not support compute shaders, but WebGPU will, and WebGPU will land shortly. As a matter of fact, I have a slide, might be the next slide. Let's see if that's coming up. Yes, the next slide. So this is very new work. We just in the last few weeks have completely rewritten the pipeline in Wigzel, which is the WebGPU shading language. And we have this running both on WGPU for native. That's the sort of the Rust implementation of WebGPU, and that's running pretty well. And we also have, as a rough early prototype, this is not ready for production yet, but it's a sign that it's in progress. We do have it running in the browser in Chrome Canary. It's not turned on by default, but if you turn on the flag, you can run our example. And so this is advanced compute. I mean, like we've had to overcome a lot of issues. We've been filing bugs against both WGPU and the web GPU standard and some other stuff, just because we're kind of on uncharted waters to some extent. And so there's a lot of work under the hood to make this work well, but we're doing that. And I'm very excited because I feel like that work will bring up the entire ecosystem. And actually, this is one of the things that I'm really most excited about is, you've got Bevy writing their games in WGPU, and it's like, let's bring these together. Let's have really sophisticated 2D rendering capabilities that are available to Bevy. I want to do a little quick demo. Let's see. This is going to be in the Pete Wixel example. All right. Okay. So this is just the demo. It's not really slick. This is kind of engineering demos. But that is something that's showing the kind of text scaling. It's also showing the new alpha blend group capability there. Let's see. This is a demo of all the different blend modes. This is the same thing as on the Mozilla MDN page that explains how the blend modes work. Classic Tiger image. You got to have that. 2D graphics. So this is a little demo showing the gradients and the fact that we can apply transforms separately on the gradient as the geometry. And so yeah, these are different things that actually are showing off different clip modes and so on. So that's just a quick little demo of piet-gpu. We're going to be doing a lot more work of richer demos and stuff like that. Let's see. Go back to slideshow here. Cool. So yeah, I wanted to talk a little bit about this idea of the paint method generating a scene fragment. And so traditionally, you're taking a render context in a mutable render context. And usually you have some other mechanisms in place, like in Flutter, you have these layers and these repaint boundaries. So if you have content that's not dynamically updating, then you want to render those to a texture. Here we're really kind of generating a scene fragment in the paint method, and so you're not re-rendering the same stuff all the time. Like if the widget isn't updating, then you're not going to call paint again. You're going to use the same scene fragment that you rendered before. You can farm this out to multiple threads, and maybe we'll have a way of updating a scene fragment. I mean, it is a fairly simple value type, so you can imagine like going in there and just changing like a color, or changing an opacity. But maybe just re-encoding, just maybe that's good enough. Maybe that's not a real performance issue. Yeah, so I did want to talk a little bit about this sort of like if you look at say all of the Apple stuff, they're very focused on compositing. You render maybe using some expensive rendering like software rendering or whatever into the layer, and then you do all this compositing. And this is a very complex trade-off, right? The goal of using compositing and the goal of doing this kind of the scene fragment approach that we're doing is the same, that you want to reduce the re-rendering work when there's no change. But there are some problems with compositing that we're trying to address. That one of the problems with compositing is that you have this variance in rendering time, that when you do update something on the first render, you have the expense of rendering into that texture, and you also have to allocate the texture. It's kind of a bump in the workload. And you also find this is one of the reasons why modern GUIs are so incredibly RAM intensive, that you have all these textures, all these intermediate textures that you're retaining, and that can add up to a lot of memory. So this is, again, like if the scene encoding is fairly compact, you upload that, and then you really don't have a lot of intermediate. There's some intermediate structures, but It's really a fairly direct pipeline from that to the pixels that come out on the other end. Um, the the compositor also kind of guides the design in particular directions. That there's certain things like translating for scrolling and sliding and doing alpha fading that are very, very easy and cheap to do in the compositor. But there are other things, like if you're doing zoom, like if you zoom the bitmap, that's cheap, but that gives you blurry results. So you kind of don't want to do that. And then other things that you don't want to do are like animation of a variable font parameter, because then you have to re-render the font, and and that's very expensive. So kind of the goal is to give you less of a performance cliff, to say, be as dynamic as you want, and we'll render it. So that's really the goal. Like we might not necessarily be the fastest render in all cases, but we are not far from that. And then the idea is any workload you give it, even when there's a lot of complex compositing, like with clips and soft masks and blends, that will do that smoothly. So I want to talk a little bit. I'm going to go slightly over. I was hoping for an hour. We'll be slightly over. Hopefully that's okay. I want to talk a little bit about the widget tree. So this is actually a pretty traditional retained widget architecture. And one of the reasons, this is a complex question. That I know that immediate mode GUI is, eGUI in Rust is definitely one of the more interesting, more advanced, toolkits. But we chose retain widgets for some reasons, and one of them is to support accessibility well. Another thing that I wanted to talk a little bit about, because it's interesting, is the layout architecture. So the layout that we have is inspired by Flutter. It's basically, we're planning on doing exactly the same layout essentially as in the existing Druid toolkit. We explored a more SwiftUI-like layout approach, kind of decided against it, decided to keep the Flutter one. But one of the interesting things, I think there's pieces from that exploration that we'll port back. And I think one of the most interesting is Geometry Reader, where you actually have sort of a dependency edge. You can really think about this as a generalized incremental computation engine, that as you change the layout in the widget tree, you get a dependency edge where that data can feed back into the app logic. And then the app logic can do any logic it likes in, all these kind of responsive UI ideas of how it wants to update its layout in response to those changes. So one of the other things that I wanted to talk about, like this is exciting because this is new work, is the AccessKit integration. And so AccessKit is a portable abstraction layer over the platform accessibility capabilities. And so we now have, and I say we, this is mostly work by Matt Campbell. I really want to give him credit for this. But it has Mac and Windows backends working in fairly decent shape. They're not complete, but they're a very, very good start. And the Linux backend is in progress. It's written in Rust, but part of the goal of the project, this is not just specific to Xilem, that the goal is to, for everything that needs accessibility, to have this as an option to bind in. And so there are bindings for other languages, and there's a bunch of other work of trying to get other projects to integrate with this. But our goal is for this to be baked in, like when we're kind of booting up Xilem as a reboot of Druid, like I want the accessibility to be baked in from the start as opposed to something that you bolt on afterwards. So part of this, like, and again, like this is one of the reasons, like this version of the talk is called High Performance UI as opposed to just High Performance GUI, because this is a performance requirement that's different than just drawing things fast. So we want to lazily instantiate the accessibility tree. So if you don't have accessibility technology connected, if you don't have a screen reader on, you're not paying for it at all. But then when you do, it calls into the AccessKit tree method, and this basically says, give me a tree, a complete tree. So this is kind of like on startup. And then when you have incremental update, every time you do a mutation to the widget is going to call this update AccessKit if active. So that takes a closure. So it's not going to do anything if there's no accessibility technology connected. There's no cost. But then if there is a screen reader, then it calls into the closure, and the closure causes the delta to update to that tree. So this is a different approach. This is a more performance-focused approach that the eGUI integration and the prototype Druid integration really built the entire tree and then diffed it. I'm going to do a demo. This is a little bit of a risk. I want to see if I can do this. So this is, I'm actually going to show the demo that I'm going to do is of eGUI. All right. And let me see if I can do this.
Voiceover on terminal. Hello_world, ZSH, 78CR, N, error, no space, N, run, new, finished F, on application. My eGUI app window. My eGUI application text. You are currently on a text element.
All right. So you hear the screen reader operating there. So this is VoiceOver on Mac. I've also experimented with Narrator and NVDA on Windows.
Arthur, your name, text. 35%, age slider.
So I can use.
You are currently on a slider. To start interacting with the slider, press Control, Option, Shift, down arrow.
So I can use the keyboard, like the tab keys and so on and so forth. I'm going to use the arrow
35.8%, 43.3%.
Now, one of the things I'm noticing is that the DPI seems wrong here.
44.2%, 45%.
Of the annotation window, but these are all things that can get fixed. So then, if I click
45.8%, 46.56, age stepper.
Or change.
You are currently on a stepper. To begin interacting with the stepper, press Control, Option, Shift, down arrow.
Great. So this is just a demo that, this is an integration with eGUI, and I can also show, let me actually
Base, RAPH, at Raphael /. You are currently on a text area, inside of a scroll area. G-I-B, G-B, G-A-A, space, X, C, K, A-R, G, cargo, A, X, C, K, new line, accessed, cargo, hyphen, E-A, feature, A, C, finish application. Hello world window. So checkbox 1, unchecked checkbox, has keyboard focus. You are currently on a checkbox inside of a group. To select or deselect this checkbox, press Control, Option, Space. To exit this group, press Control, Option, Shift, up arrow.
I'm sure there's a way to set that to be less chatty. But this is interesting because this is a demo in the Glacier. Glacier is the sort of platform integration layer. It takes over from Druid Shell. And this is an example that has no drawing. It's sort of the opposite of the way UI usually works, where there's drawing and no accessibility. This one has accessibility and no drawing.
Checked, checkbox 1, checkbox 2, unchecked checkbox. So, you are currently on a checkbox inside of a group. To select checkbox 2, unchecked checkbox.
So again, let's see, where was I? This is an integration with Glacier, and this just landed in the last week or so, and I'm really looking forward to building this out. All right.
Authentication. Login, enter password. System dialog. Your screen is being observed. Friday, December 2nd, 8:59 a.m. Touch ID or enter password. Application. Okay. Hello world window. In system dialog. Content voiceover off.
Okay. All right. Okay. Yes. So I'm, as I say, I'm just really excited about having accessibility in there from the beginning, and really, really looking forward to working with Matt to get these integrations to be smoother. And I think I ended up pressing the Touch ID. And this is evidence that I need to practice my accessibility demos more smoothly, because it is not something I'm used to doing, and you saw how rough that was. But it's a good reminder. Like, accessibility is hard for people who have visual impairments, and so we really want to make that a good experience. All right. So I want to talk a little bit about a layered architecture. And so, we are thinking about this from top to bottom, like when writing these reactive components and then having that come down all the way to the rendering of pixels with the GPU rendering. But you might want to take one of those abstraction boundaries and cut at a different place. And so there's this bottom layer, which is the GPU accelerated 2D rendering. And it's very easy to imagine that people will want to take that and use it for different applications. Like, for example, in a Bevy integration, maybe you're doing a 2D game. Maybe you're doing a game like that kind of has the same visual style as Mini Metro or something like that, where you have a lot of 2D graphics that you want to draw. And I would love for people to take that part of the stack, and you don't need to worry about the widgets and stuff like that if you're primarily focused on just drawing 2D graphics. There's middle layer, the retained widget tree, that isn't depending on. So earlier there was a question about the difference between the widget trait and the view trait, and one of the answers is you can do the widget trait without a view trait. You could drive the widget trait manually. That would be really painful because you have to, knowing how to update, how to mutate is very tricky. I would almost never want to program that manually, but it is very easy to imagine connecting some other, either reactive UI, or maybe you're connected to a scripting language where you write your UI in Python or JavaScript or something like that. And, that ends up driving the widget tree from this system, right? And then the top layer is the reactive architecture that is very REST-centric. Like you could drive it from other languages, and we in fact have a Python. I'm not going to do the demo because we're way over time, but we do have a Python demo that drives the REST reactive architecture, and that works because of type erasure. That when you have a Py widget or a Py view, actually it's not a widget, it's a view. That's an any view under the hood, and that makes that layer of integration work. So I think of these layers, this top one is sort of the most speculative. Like, I think there are reasons to believe that the Xilem architecture is good and will work well, but there are other architectures that have not yet been ruled out. So there's MakePad, which is an immediate mode inspired one, but it has a dual dispatch, so it avoids some of the problems. There's a number of projects out there, like Dioxys is a very interesting project. It really takes the ideas of React and re-implements them in Rust. And then there's another project called Sycamore, which is finer grained reactivity. And so I think from a technical perspective, it's very interesting. And those could be implemented on top. You could take those architectural ideas and implement them on top of our retained widget. Okay, so there's a couple of questions in chat. The difference between let's do difference between widget and view. So I'll try and do this very, very quickly. A view is a high-level declarative description of what the app wants to present. So it's got views and it's got layouts like columns and stuff like that. And it's a very simple value type. And it is not itself interacting with the platform. The view generates a widget tree. So a widget is derived from a view. You can almost think of a view as a builder for a widget. So when you have a button view, that's going to build a button widget. And then the button widget is the thing that's interacting with the layout protocol and drawing its appearance and so on and so forth. So the idea of separating these is to support this declarative reactive UI model where the details of all that UI interaction is hidden, that the app is just doing a very simple declarative, like this is what I want to show. It's got these columns with these buttons and sliders in them. And then that that simple value type view builds or updates the widget tree, which is where all the messy, complex stuff happens, kind of under the hood and kind of hidden from the app logic. So I hope that gives the flavor. There is more detail in the Xilem blog. When I'm doing desktop UI, I need advanced drawing capabilities in addition to normal 2D widgets. How would this be doable with Xilem? So this is absolutely a major goal of why we are, one of the main reasons why we ported over from our hand-rolled GPU infrastructure to WGPU. The goal, and this is future work to be done, the goal is that if you can get the result of that drawing into a WGPU texture, then we will be able to take that texture in as a, as a view or a widget, get that into the Xilem architecture, and then use that as a painting element. So then you can composite your UI over it and scroll. There's a deeper, more complex set of questions around this, but my hope is that we'll be able to get the basic version of that working pretty soon. Which branch should we look at? So there is now, it used to be very painful. It used to be this branch off of the Druid repo, but there is now a Xilem repo. And so look at that. And as a matter of fact, I will demo that right now. Okay. So you basically just clone Linebender Xilem. And then I think right now, the easiest, it's a main. And at the moment, it is very, very, very simple. What it does, it's just a button. It's the most basic demo you can imagine. But the point is that this is running on the full stack of new infrastructure. And so everything is new. The window creation is Glacier instead of Druid Shell. The painting is piet-gpu instead of Piet. The text layout is Parley, which is a text layout library that Chad Brokaw is working on. And so, it's just a button, but it's like all the stuff under the hood is doing its thing. All right, and where did my slides go? Oh no. They're there. Great. Right. So there's some things that we're not doing right now. And that's part of, how do we make this project sort of the scope of it viable? So right now, we don't have a good solution to theming and styling. I think that we have a really excellent open source community, and I'm encouraging people in that community to investigate what kind of theming and styling system do we want for this. And so I think it will get there. But right now, we're doing very basic hard-coded styling, and we're not planning on doing anything super soon on that. Animations are another thing where the goal right now is to provide the lower level capability so that we will be, if you can specify an animation, we will render it with super high performance. But how do you declaratively specify animations? That's kind of a tricky problem. And similarly, we're, to make a really good UI product, you need good design tools. We're again, for right now, just saying, just code this in Rust. And, I think there's a lot of potential to do interesting things in the future, like, for example, design in Figma and export. But right now, that's out of scope. And then the last thing, and this touches to one of the questions that got asked earlier about the sort of advanced drawing. On the longer term roadmap for this work, you want to interact with the system compositor. You want to be able to have content that's in its own compositor node, and then that compositor node is being composited by the system with the UI content that we're generating. That is a very hard problem. And it is especially difficult because it is different from platform to platform, and some systems don't have compositors. So if it needs to run on Windows 7, the compositor is optional, and if it needs to run on X11, there's effectively no compositor. Although usually there is a compositor, but there's no real programmatic way to access it. And you need to do this. If video playback was a major goal, then we might be able to get something in place where you decode the video into a WGPU texture. That is probably something we will prototype and get working, but the performance is not going to be as good as if it was actually playing into a compositor node. So there's a blog post coming up. It's been in the works for a long time, but I'm hoping to get that published. That will talk about kind of the challenges and the end goals of that. So what's the current status? Well, this is work in progress. Yes, embedded web view is another thing where you really want that to be, integrated. And so that's out of scope. We're not doing an embedded web view anytime super soon. So all this stuff is prototype. The Xilem repo that I just showed has a clickable button right now, and over the next few weeks, I'm expecting that we're going to do just kind of a massive expansion of that into porting over hopefully most of the existing Druid widgets, and getting something where you can actually express interesting UI. The piet-gpu repo, these are all linked in the slides. piet-gpu repo has the 2D drawing layer, and that's I think it's still research, but I think it's moving towards being usable. There's also a prototype of Xilem Web, using the Xilem architecture to drive web backends. I don't know that we're necessarily going to pursue that, but it is an interesting thing to explore. So there's a tremendous open source community interest. Let's see, I think there's and the next slide is better for this. So, we're going to be, I'm really hoping to get the community to build the widget tree and really not just blocking on stuff that I'm personally doing. You can follow the progress. I'm trying to blog. I'm trying to write about all the stuff that I'm doing. So it's not just this big block of code, but there's like explanation and explaining how, so people can understand how it works. The xi.zulipchat.com, that, by the way, is now web public. So you don't even need to create an account to read it, to browse it. A lot of interesting threads on there. And really encourage people, like if you wanna participate, then getting on the Zulip is a good way to do that. We've also started in the last month weekly office hours, and so those are 8 a.m. Pacific time on Wednesdays every week, and that has been a fantastic way to get the community together, to have really interesting discussions, and to coordinate the work, because this is a very ambitious project. So it's still branded as research. We're not promising that there will be a product. That a major goal is to learn. Like, I think if you want to describe the goals very quickly and concisely, it's like to learn how do you build really high quality, really performant UI. And so far, it has been quite a journey, and I'm really looking forward to continuing it. So that's the slides. And I would be happy, I don't have a time constraint, but let's see how many questions we get. I'm happy to answer questions that people have. Type them into the chat. And I suspect if I save a VOD, we'll see how this works. If I save a VOD, I think the chat is preserved. But if I do the YouTube video, I'm not sure. We'll see. Can see the Python demo. Okay. This I did not practice. So let's see what we have. This could be exciting. Switch. Why is this not working? No module named foo. Okay, that's exciting. I think I can Xilem 1.0 when. So there's a question in the chat. Xilem 1.0 when? The answer to that is it's up to you. If we get tons and tons of contributors that are really bringing a lot of energy of building all the pieces, then we'll get Xilem 1.10 in an interesting time frame. If not, then it will take a while. So this is an open question. All right. Libvideo path dot dilib. I have to remember how to do this. Build debug. Oh, come on, debug. Okay, I'm not sure I have this. And this is called, I think, foo.so. Have ARM86 need x86 64. I think that I'm not going to be able to do this demo today. It's something I should have had prepared and practiced. Have ARM need x86 64. Why is my Python 3? Let's see. I might be able to do this. Anaconda. That's probably the problem. So where would be another Python 3 if I don't have the Anaconda one? Ha! Ha ha! Excellent. Great. Fantastic. So this is the thing running, okay? And that's not actually the interesting part because that's a really boring demo. The interesting part is, let's see, I did this the wrong way. I wanted to expand the size, the font size, but not the window size. 80 by 24. So the interesting part is this. This is the Python code that did that. And so it's super, super simple, basic code. And then it just imports, it's called foo because that's the best name for importing a UI toolkit. This is the complete Python code that runs that. So it's just creating one of these view trees, and then when you do like foo.button or whatever, that's internally a PyView. Yes, it's very similar to the Rust code, but the difference is that it's type erased, right? The Rust code was statically typed. So this thing had a type of like column, of like button and label, whereas this code is a PyView. Everything is a PyView. It's all built with Py-o3. And so again, I'm pretty excited that this was one of the architectural limitations that Druid really could not be driven from Python. And I think that this is evidence that the Xilem architecture is more flexible, that you can in fact say, hey, let's type erase the types, and make that work. So it's evidence we have a better architecture, I think. All right. More questions. They're good ones. Is there a plan to allow for Wigzel filters in the widget tree, like allowing a blur filter, for example? So first of all, these are two questions. So the first thing is that, yeah, we definitely are going to have blurs in piet-gpu. We don't have that now. It's complicated because you need to build a render graph. You can't, like, everything that happens now is done in the fine rasterization step. So you can do blends, you can do all this stuff with gradients. There's a lot of stuff you can do in that. Like, I'm actually interested in things like watercolor and paint strokes. You can do all that in fine rasterization. You can do a lot of shader effects in a compute shader for fine rasterization. But for blur, you need a render graph. You need to be able to render into an intermediate texture and then write another filter that takes that texture and does some other computation. So we'll have blur. Now, in terms of general Wigzel filters, that's an interesting question, and I would put that as like a potentially interesting research direction. Like if we have a really compelling use case, or it's the same question as before. Like, either we have a compelling use case to do sort of general, like, hey, just bring your own, write your own filter and just arbitrary Wigzel, or somebody has the energy to bring that. Like if you really are excited about that feature, then figure out how to build it and add it. Okay, question from Matt Campbell. On the question of transforms in piet-gpu, what happens when you insert a line in the middle of a multi-line text block? Do you have to re-encode the subsequent lines just to update coordinates? And he's also thinking about how you handle that in AccessKit, and right now you have to update the subsequent nodes. This is a really good question, a really deep question. My personal feeling is that you absolutely need to have incrementality of text at a granularity of paragraph and larger. So if you have so paragraph is also like logical line. So if you have like code, then each line of code is its own paragraph. So you definitely want it so that when you if you insert a line, then those lines don't get laid out, re-encoded at all. You just update their coordinates. And ideally, it would be nice. Like, I haven't looked at the AccessKit thing. If you could apply a group transform, or if you could just say, I just want to update a position, on that node without changing the contents, that would be the right way to do it. At a granularity finer than paragraph, I am not convinced that it's worth doing better than just rebuild the whole thing, because the complexity goes up. And if you're saying, yeah, you're going to relay out or re-render, a single logical line, I think you can almost always do that within interactive time constraints. So I hope that answers it. In Druid, you can only have a global state. Have we thought about components having their own state similar to React? Yes. So again, look at the Xilem blog. It addresses this. So there's this adapt node, which actually allows. It's also not strictly true that you can only have a global state in Druid, but it is painful to do more complex state management in Druid. So the goal is, yes, that components, you can have components, and components have their local state, and the adapt node is what does that. The DPI bug for voiceover, yes. Well, yeah, and this is a thing where this is something that everything you're seeing here is very early prototypes. It's very much work in progress. None of this stuff is finished, and so hopefully we'll see it evolve, and it's a great opportunity for people to pitch in. Like, if you're a user and you saw a problem like that, then file a bug, and hopefully we'll get on it and fix it. Current effort. So I mentioned Bevy earlier. Is there a current effort to integrate Xilem Druid? I don't know. I mean, I want to have a conversation with Cart. Like, we've interacted a little bit, and we both have the intent of seriously talking about this stuff, but it's early to say. There's no current effort, no, but I'm interested in exploring that. Will Xilem have something like mouse events bubbling? So that's a really interesting question, because bubbling, I think of bubbling as being very much a web approach to this stuff, and I think of the web approach as being very heavyweight and a little bit messy. So the current answer is, we have a event dispatch and propagation mechanism that's in Druid, and the current plan, and it dispatches mouse events to the widget that should be receiving them, and I think it works pretty well. And so the current plan is to just port that over. But it is always an interesting question about what richness does that lack? How might you do things in a richer way? Maybe some form of bubbling. So, but there's no current plans to do the full DOM bubbling event bubbling protocol. Sweet. Those were good questions. I don't see any more popping up in the chat, so I think I'll end the session right now. I want to thank everybody again for attending. Thanks the people that asked questions, and I am hoping to see a bunch of you on in our community spaces. So, thanks and bye.